So, welcome to lecture series on mathematical methods and its applications. So, we have already discussed Fourier series, Fourier integrals and Fourier transforms. Some problems based on that we have already dealt with. Now, let us come to applications of Fourier transforms to BVP. So, in this section we will also include applications of Fourier series and Fourier integrals also. Okay. Now, equations involving one or more independent variables are called partial differential equation, this we already know, and such equations frequently arise in various engineering and science problems. Some important linear partial differential equations of second order are as follows, that we already know that one dimensional wave equation is given by this expression, one dimensional heat equation is given by this del u by del t equal to c square del square u upon del x square. Two dimensional Laplace equation is given by this del square u by del x square plus del square u upon del y square equal to 0. Two dimensional Poisson equation is given by del square u upon del x square plus del square u upon del y square equal to f x y. Similarly, two dimensional wave equation is given by this expression and three dimensional Laplace equation is given by this expression. Okay. These are the important partial differential equations. Now, how can we solve a given partial differential equation using Fourier series? First of all, we see using Fourier series. Okay. So, we use separation of variables. Now, suppose a partial differential equation is given to you, any partial differential equation, it may be a one dimensional wave equation or one dimensional heat equation or two dimensional wave equation or anything. So, how can you solve it? You assume that u x t, which is a function of two independent variable, is simply f x into g x, f x into g t, this we assume. So, we basically adopt this method which we call as separation of variables. Okay. Now, we find del u by del x, what it is? It will be nothing but f dash x into g t, because this function is only a function of t. Okay. Suppose you find del u by del t, so that will be nothing but f x into g dash t. So, del square u by del x square, that will be nothing but f double dash x into g t, and similarly del square u by del t square will be nothing but f x into g double dash t. So, okay. Now, we substitute this in the given partial differential equation, whatever partial differential equation is given to us, we substitute these values in that equation. Now, when you substitute this in that given partial differential equation, we get back two ordinary differential equations which we can easily solve. Now, we apply initial and boundary conditions whatever given to us, and hence we can find u x t using Fourier series. Okay. Then using Fourier series we can find u x t. So, let us illustrate this this method by some examples. Okay. So, this is all we have discussed. Now, first of all, consider one dimensional wave equation using Fourier series. So, consider an elastic string of length L which is fastened at its ends on the x axis at x equal to 0 and x equal to L. The string is dispatched and then released to vibrate in the xt plane, where u x t denotes the vertical displacement of the vibrating string. So, u x t is nothing but the vertical displacement of the string. So, the differential equation governing this is given by, what is differential equation governing this? It is nothing but del square u by del t square is equal to c square del square u by del x square. So, it is x is varying from 0 to L and t is greater than 0. Okay. So, these are the boundary conditions, the initial conditions given to us. Okay. Now, we want to solve this this partial differential equation which is one dimensional wave equation. How can we solve it using Fourier series? So, we assume that u x t is nothing but a function of two variables, a function of product of two functions f x into g t. So, what will be del square u upon del t square? it is nothing but fx into g double dash t. And what is del square u upon del x square? It is nothing but f double dash x into gt. Okay. You substitute these these things over here. So, what we obtain? It is f into g double dash fx into g double dash t, which is equals to c square f double dash x into gt. So, this implies f double dash x upon fx is equal to 1 upon c square times g double dash t upon gt. Okay. Now, this is a function of x alone and this is a function of t alone, and both are equal. So, both will be equal only when it is equal to some constant, say k, where k is a constant. Okay, because one side we have a function of x and other side we have a function of t, and both are equal. So, both will be equal only when it is a constant quantity, say k. Okay. Now, this k have three possibilities, either k is 0 or k is positive or k is negative. Now, let us take all the three cases. Case 1, suppose k is 0. Okay. If k is 0, so f double dash will be 0. Okay. F double dash x will be 0, and this implies fx will be nothing but ax plus b, where a and b are arbitrary constants. Now, using the boundary condition, when you use the boundary conditions, what are boundary conditions? Okay. See the boundary conditions. It is u0 t is 0. So, this implies when uxt is fx into gt, so it is nothing but f0 into gt is 0 and is 0. Now, ult is also 0. So, this implies fl into gt equal to 0. So, from these two conditions we get either this equal to 0 or this 0 or this 0 this 0. Okay. Suppose gt is 0. If gt is 0, so u will be 0, which is not possible, which is of no interest, because u must be non-zero. Okay. gt can't be 0, because if gt is 0, then u will be 0. Okay. Now, this implies f0 will be 0 and fl will be 0. Now, when f0 is 0, when you apply this over here, f0 equal to 0, so this implies b equal to 0, and fl equal to 0, this implies a equal to 0. So, that means f equal to 0, and when f equal to 0 means u equal to 0, again which is of no interest. Okay. Because we want u as a non-zero function. Okay. So, now case 2. So, this case is not possible, because from if we take k equal to 0, we are getting u equal to 0, which is of no interest. Okay. Now, case 2, suppose k is equals to a positive quantity, suppose p square. Suppose k is some positive quantity p square. If k equal to p square, so this implies f double dash will be equal to k into f, and this implies d square minus k into f. Oh, k is p square. Okay. K is p square. So, this is p square. So, this equal to 0, and this implies f will be nothing but c1 e ki power px plus c2 e ki power minus px. Now, again f0 equal to 0. So, this implies c1 plus c2 equal to 0 and fl equal to 0. So, this implies c1 e ki power p plus c2 e ki power minus p equal to 0. So, when you simplify these two equations on c1 and c2, so this implies c1 equal to c2 equal to 0. So, hence f equal to 0, again this implies u equal to 0. So, this case is also not possible. So, take the third case, case 3. when k equals to minus p square. So, these are the only 3 cases, either k is 0, k is positive or k is negative. If k is 0, we are getting u equal to 0, which is not possible. If k equal to p square, matlab positive quantity, again we are getting u equal to 0. And if k equal to, now let us try for the k equal to minus p square, okay. If k equal to minus p square, f double dash will be nothing but minus p square k. So, this implies d square plus p square times, okay, f, okay, f will be equal to 0. So, this implies f will be nothing but c1, so it is cos px plus c2 sin px, okay. Now, when f0 is 0, f0 is 0 implies c1 equal to 0 and fl equal to 0 implies 0 equal to c2 sin pl. Now, if c2 equal to 0, again f will be 0, which in turn gave u equal to 0, okay. So, that case is omitted. So, this implies sin PL will be 0, because we do not want C2 to be 0, because if C2 is 0, F is 0 and which in turn give u equal to 0, okay. So, sin PL equal to 0. So, this implies PL equal to n pi or P equals to n pi by L, P equal to n pi by L. So, this is the only case possible, and from this case what will be f? What is f? F will be nothing but C1 is 0 and we have C2 sin P is nothing but n pi by L into x. So, since n is involved, so we take it Fn or we take it Cn, here also we take it Cn, okay, because n is involved. For different n we get different f, so we are calling it Fn, okay. Now now for this p, for this k, where k equal to minus p square, find g. What will be g? So, it is g double dash will be equals to, it is minus p square c square g, because k is nothing but minus p square. So, from here again we will get g as suppose something d cos p c t plus e sin p c t, okay, where d and e are arbitrary constant. Now, this p is nothing but pi n pi by L. So, when you replace, you call it dn gn and dn cos n pi c t by L plus en sin n pi c t by L, because n is involved. So, we are calling it dn and en, and here we are calling it gn. So, what will be u now? So, what will be u? Now, this u is nothing but product of f and g, okay. So, we are calling it un. So, it is nothing but fn into gn, and fn is nothing but cn into this quantity. So, this constant will merge to dn and en. So, finally, we will get sin n pi by L into x into dn, the new dn, suppose dn dash cos n pi c t by L plus en dash sin n pi c t by L, okay. Now, this is n may be 1, may be 2, may be 3, and all are the solution of this differential equation. When you substitute n equal to 1, you get one solution, that is a solution of this differential equation. When you substitute n equal to 2, so u1, u2, u3 up to so on and so on are all the solution of this given differential equation. So, we know that by the superposition principle, if u1, u2, u3 and so on are the solution of a given differential equation, then the linear combination of those will also be the solution of the given differential equation, given partial differential equation. So, what will be the, so we suppose u x t as summation n1 to infinity u n x t e, which is nothing but summation n from 1 to infinity sine n pi x by L into dn dash cos n pi c t by L plus E n dash sine n pi c t by L. Okay. So, this will be the solution of this differential equation by the superposition principle. Now, let us apply initial conditions. Now, u x 0 is f x. So, u x 0 is f x, which is equal to summation n from 1 to infinity. When you substitute t equal to 0, so when you substitute t equal to 0, we get back to this expression. Now, this is nothing but Fourier sine series. Okay, this is nothing but is equal to Fourier sine series, half range Fourier sine series. So, from here what will be dn dash? So, dn dash will be nothing but 2 upon L integral 0 to L f x sine n pi x upon L into dx. So, this is by the Fourier series. Okay. So, basically dn dash and en dash is to be find out finally. Okay. So, to find dn dash we take this boundary condition. From this boundary condition we get this equal to this. This is nothing but a sine series, Fourier sine series. Okay, Fourier sine series, half range Fourier sine series. So, from here we get dn dash as 2 upon L 0 to L f x sin pi x by L into dx. Now, to get E n dash we apply another initial condition, which is del u by del t at x comma 0 is gx. So, this implies, now what is del u by del t? Del u by del t is nothing but when you differentiate respect to t. So, this will be sine, which is 0 when t equal to 0, and this is cos which is 1 when t equal to 0. So, we finally obtain gx is equal to summation n from 1 to infinity E n dash into n pi c by L into sine n pi x upon L. Okay. Because when you take when you differentiate partial respect to t and put t equal to 0, so this is sine which is 0 and this is cos which is 1. So, only the coefficient will come here. Okay. Now, this is again Fourier sine series, half range Fourier sine series. So, the constant term which is this term, the entire term, this implies E n dash into n pi c upon L will be nothing but 2 upon L integral 0 to L f x sine n pi x upon L into dx. So, L cancel out. So, from here E n dash will be nothing but 2 upon n pi c integral 0 to L f x sine n pi x by L into dx. So, these are the values of dn dash and en dash, which when substitute here you will get back to u x t, which is solution of this partial differential equation. So, hence using Fourier series we can solve such type of problems. Okay. Now hence find the solution of one dimensional wave equation, which is this problem corresponding to a triangular initial deflection. Suppose the u x 0, which is f x, is given by this expression and the initial velocity is 0. Initial velocity is 0 means this we are calling as del u by del t, which is nothing but the initial velocity at t equal to 0 means initial velocity is 0 means g x is 0 and f x is given by this expression. So, we can easily find out if g x is okay, here it is gx, sorry, because it is equal to gx, so it is gx, sorry, it is gx. Okay. Now, if gx equal to 0, so E n dash will be 0, so E n dash is 0. Okay. And to calculate d n dash, so we know that f x is given by that expression, we simply substitute f x over here, find out d n dash, and we substitute d n dash over here, we will get back to the value of u x t. So, this integral we can easily find out. Okay. Now, come back to next problem, It is a heat equation, again solution by a Fourier series. Consider a thin homogeneous bar of wire of length L. Let the bar coincide with the x axis. So, we have a bar basically which coincide with x axis. So, this is some bar of length L. Okay. Now, u x t be the temperature distribution within the bar. The boundary value modeling of this temperature distribution u x t is given by this. So, this is nothing but u t equals to c square u x x, where this is a finite bar of finite length and t greater than 0. So, these are the initial and boundary conditions given to us. First find u x t. Okay. First find u x t means find the temperature distribution of the bar, if these are the initial and boundary conditions. So, again we will apply separation of variables. We will take u as f x into g t, we will substitute it here. So, it is g dash t into f x is equals to c square f double dash x into g t, which implies f double dash upon f is equals to 1 by c square g dash upon t. Again it is a function of x, it is a function of t, and both are equal. So, both will be equal only when it is a constant quantity, say k. Okay. Now, again we will take 3 cases. So, the boundary condition are similar to the previous problem. Okay. It is 0 at both the ends when x equal to 0 and x equal to L, it is 0. So, it is similar to the previous case, one dimensional wave equation. So, again when k is 0, u comes out to be 0, and when k equal to p square, u again come out to be 0. Since boundary condition of this problem and the previous problem and this problem are same, it is also 0 when x equal to 0 and x equal to L, and it is also 0 when you x equal to 0 and x equal to L, since boundary condition are same. So, when k equal to 0 or k equal to p square, u comes out to be 0. So, we do not take these cases. So, take k equal to minus p square. So, solution will exist only when k equal to minus p square. Okay. So, when k equal to minus p square, f double dash upon f will be equals to minus p square, which is implies f will be equal to c1 cos px plus c2 sin px. Again f0 is 0, this implies c1 is 0, and fl equal to 0, so this will imply c2 sin pl equal to 0, and since c2 can't be 0, because if c2 equal to 0, again f will be 0, which in turn gave u equal to 0. Okay. Because if f equal to 0, then u will be 0 and u can't be 0. So, this implies PL will be n pi, and this implies P will be n pi by L. So, from here we will get Fn equal to sine n pi L by x. Okay. Now, we get back to here this expression. So, what will be g dash? So, g dash will be nothing but minus p square c square g. When you integrate, it is first derivative only. So, when we integrate both sides, it is log g, which is minus p square c square t plus log some k, which implies g is equals to k e की power minus p square c square t. Now, when you substitute p equal to pi n by L, so it is nothing but we got it gn and it is kn e ki power minus it is a pi n pi by L whole square into c square t. So, Gn will be given as kn e ki power, suppose it is minus lambda n square into t, where lambda n is pi this expression. Okay. So, what will be un now? Un will be fn into Gn. So, the multiplication of these two will be nothing but this gives kn into sine n pi x upon L into e ki power minus lambda n square into t. Now, again by the superposition principle, u x t, which is solution of this differential equation, will be nothing but this partial differential equation. So, u x t will be nothing but summation n from 1 to infinity u n x t. So, which is nothing but summation n from 1 to infinity u x t is k n sine n pi x by L into e ki power minus lambda n square into t, where lambda n is n pi c by L. Now, apply the initial condition that u x 0 is equals to f x. So, this implies f x is equal to summation n from 1 to infinity k n sine n pi x by L. Now, again this is a Fourier sine series. Okay. So, hence k n will be given by, so this implies k n will be nothing but 2 upon L integral 0 to L f x sine n pi x by L into dx. So, if you substitute this k n over here, so we will get the solution u x t of this partial differential equation. Okay. Now, also find the solution of the boundary condition are replaced by the condition that both ends of the bar are insulated. So, the problem is same, in the same problem the boundary condition, which are these conditions, are replaced by the condition that both ends are insulated, that means no heat is passing through both the ends. Okay. So, what does it mean? It means that now the boundary conditions are u x at 0 t equals to u x at L t are 0. Okay. These are the new boundary condition for this problem. All other conditions are same. So, what will be the solution of this problem under these boundary conditions and initial conditions? So, again we will substitute u as the same thing f into g, f x into g t. So, we will get back to f double dash upon f, which is equals to 1 upon c square g dash upon g, which is we take as k. K can't be k is the only possibility is k equal to minus p square, that we have already discussed. So, k equal to minus p square. So, when k equal to minus p square, f double dash will be equals to minus p square f, which implies f is equals to c1 cos px plus c2 sin px. Now, from here what will be u x? U x will be f dash x into g t, and u x at 0 t means f dash at 0 into g t equal to 0, and u x at L t means f dash L into g t equal to 0. So, g t can't be 0, because if g t equal to 0, then u equal to 0, which is not possible. So, g t can't be 0. So, this implies f dash 0 is equal to 0 and f dash L equal to 0. So, when we apply this thing over here, so what we will get? So, we will get now f dash, what is f dash? It is minus p c1 sin px plus P C2 cos Px, and f dash 0 equal to 0 implies C2 equal to 0 because P can't be 0, and f dash L equal to 0 implies minus P C1 sine PL equal to 0. So, this can't be 0 because if P is 0, K equal to 0, that case is already omitted, and if C1 equal to 0, then C2 is already 0, then F will be 0. This implies U equal to 0, which is also not possible. So, the only possibility is sin PL equal to 0. If sin PL equal to 0, so PL will be equal to n pi. So, P will be nothing but n pi by L. So, from here F will be nothing but, or Fn will be nothing but cos P n pi by L, cos n pi by L into x, substitute the value of P, okay. And Gn is the same, Gn is the same. What will be Gn? What G we obtained in the last problem, Kn e की power minus lambda n square into T, where lambda n is nothing but n pi C by L, okay. So, what will be U now? Un will be nothing but Fn into Gn, so that will be nothing but Kn cos n pi L into x into e की power minus lambda n square into T, okay. So, again by the superposition principle, what will be the solution? So, the solution will be nothing but u x t will be nothing but summation n from 1 to infinity u n x t, which is nothing but summation n from 1 to infinity, it is k n cos n pi x by L into e की power minus lambda n square into T, where lambda n is n pi C by L, okay. Now, apply the same initial condition, that u x 0 equal to f x. So, this implies f x will be equal to summation n from 1 to infinity k n cos n pi x by L. So, now it is a Fourier sine series, I mean cosine series, okay. Here is a cosine series. So, then k n will be nothing but 2 by L 0 to L, it is f x cos n pi x by L into dx. So, when you substitute this k n over here, so we will get back to the solution u x t, which is a solution of this partial differential equations. So, hence the partial differential equation can be solved using Fourier series, okay. So, these are the some applications of Fourier series which we have discussed here. So, that is all for this lecture. So, thank you.